Our next presentation is from Chris Heistand of Johns Hopkins Applied Physics Laboratory. And he will be talking to us about DART, DevOps Report Card. Chris.
Hi, everyone. Can you hear me?
We can hear you and we can see you.
Awesome. My name is Chris Heistand, and I am the DART Flight Software lead. And I am indeed going to give you a report card on our DevOps strategy. Next. So I wanted to first kind of orient everybody with what is DART, our environment evolution as we've gone through the spacecraft, the general flight software architecture, and what is DevOps, because everybody has their own definition, and then really dig into the meat of how we explored DevOps and what was good and what was difficult. Next. So some system orientation slides to get you oriented. Next. DART is the double asteroid redirection test. It has a single goal, and that is to move an asteroid. So we are a spacecraft that is targeting the Didymos binary system. It's two asteroids, a much larger one, 700 meters, and a smaller one, 160 meters. Dimorphos is the smaller one that is orbiting the larger one. We are planning to build a spacecraft and crash into that asteroid as fast as possible and change the orbit period. We're going to be using orbital nav, optical nav, sorry. So we have a camera / telescope at the front of our spacecraft that is going to help us hone in. And before we impact, we are popping out a CubeSat from Italy, and they are going to watch us on our ride in. We should be able to change the orbit period such that the light curves from Earth for the entire system can actually be measured. And so the whole goal is to basically see if we can deflect an asteroid if it was actually coming to Earth, which it is not. But you got to test it before you hit the real thing. Next. We are entering TVAC this week. So we are at the very end of our late life cycle, but we started with just a couple of containers and a software emulation. So we started with CFE, so we're built on top of CFE, but we started with PC Linux. We've moved to RTEMS. We started with testbed software. We've moved to a spacecraft and real hardware. And we started with ground software. We started with Cosmos and have moved to L3, and I will hit on that point later. But essentially, you have a fidelity increase as you move through your life cycle. And that it's really important to understand what you're changing as your fidelity increases and how good your models are in the beginning, so that your tooling actually works all the way through. Next. From a flight software perspective, we have a generally traditional software architecture for APL. So it is built on the CFE, Goddard CFE, on top of RTEMS. We're running on a UT700. This seems to be a generally common stack for people. We have an RTG4 that is basically hard Leon paired with FPGA fabric. All of our messages and all of our control is over SpaceWire. Our software stack itself that you can see on the left, all the blue applications, we were able to pull heritage. So we got these from Solar Probe, from Van Allen probes. And the red applications, they're basically the new applications. So the exciting ones are things like DCIU, which is our NextC ion propulsion controller, or Imager, which is the control for the Draco, which is our telescope camera that helps hone us in. Next. And lastly, I wanted to try and give you a DevOps overview. So DevOps means something different to every single person. Overall, the goal for DevOps in our mind is to get feedback faster, actionable feedback as fast as possible. So what that means to us is we picked 4 specific tenets: small bytes, data deduplication, visibility, and tightening the feedback loop. We're going to walk through each one of those individually, but you will see an emphasis in the rest of the slide deck. The spacecraft is a very large, complex, moving state space, especially as development happens, especially as you walk through that development cycle, going from emulations to real hardware to real spacecraft to on-orbit ops. And the goal that we see DevOps and these tenants providing is an ability to understand and move through that state space in a better way. So we're going to try and break out each one of these and tell you how it worked and some of the pros and cons. Next. Okay. So to orient you, basically these are in 2 slide packages. First slide, it is overview of the tenant, brief description, talk about effort versus effectiveness with that graph. And then second slide, we talk through some key points and takeaways. So the big thing on small bytes, the goal is to have checkpoints where you understand the state of the system, but the tenet of small bytes is shortening the checkpoints and condensing the amount of change that happens between one checkpoint and another. So it is sampling at a faster rate and sampling at a simpler rate. So this includes branching so that I'm only taking in my changes and not somebody else's changes, and able to test that, understand that, and then say, yes, this is ready to go. The thing that I like to, the story kind of is, if you have something that is being checked in to a main branch every week, versus a handful of developers that are working on 3 separate things and checking in every day, if something fails on each one of those branches, it's easy to roll back and understand what's going on. If you are trying to backtrack a week's worth of code tangled between 3 developers, that becomes really, really hard. So for this, there's a couple of things that help you get there. So from a philosophy's perspective, commit early and often. I'm sure that you have heard that. Branch per ticket. There are tools like Git, Bitbucket, GitLab. It's pretty low effort to do small bytes, and it is generally very effective. You can, if you can get a team to adopt this this kind of philosophy, it becomes immediately useful, and it is a multiplier, because the time sample that you are looking at that state space is important to how well you understand it, up into a point. So next step. So it is important until you have that drop off of oversampling. So basically you can get to a point where you are sampling, instead of saying, hey, I have a check-in for this small chunk of code that's been a couple hours of work. If you check in every single character, well, you're just burning resources, and that's where that drop off happens. So basically the big takeaways: small bytes are really important for rollbacks and understanding what happens from point to point. Branching CM systems are really important. And you need to think about checkpoints, not just for flight software, but from a system-wide perspective. It's not just your flight software code. It is your data definitions. It is, or your packet definitions. It is your hardware, the emulations that you're running on. All of that configuration needs to have some sort of understanding of, I'm at this checkpoint, what is going on in that system, and be able to understand the small changes going into it. Next, data duplication or data deduplication. So every team deals with this. You start with a requirement. Let's say you have 15 spacewire messages maximum per second. Then you put that number in code. Then you put that number in your test. Then you put that number in your workbook, your docs, your ICD, your test bed, every single time you replicate that number 15 via a human action, you have another place that your data and your state can tear across the entire system. So if it changes in one place, it's supposed to change in all, but what if some human misses that? Data deduplication is that concept of getting that single number 15 only in one place and propagating it automatically everywhere else. So whether that is a hard link, whether that is an auto generation, whether that is some other machine tie, that is the goal. So it is also a multiplier like small bytes. It's really, really hard to actually detangle things that have already propagated. So if you are starting with a bunch of code and a bunch of requirements that already have this one number copied everywhere, it's hard to consolidate and put it back in the bag. But it is actually really easy if you start with it. And so that's where you can see that effectiveness versus effort, the after the fact versus the from the start. Next. So the big thing here, aim to get your magic numbers and definitions to exist only in one place. That is essentially all of this boiled down. The data needs to be human and machine readable. I think that is also something to be very aware of. You want your source to be PRable, so like being able to look at it in a pull request, but also you want it to be able to be read from a machine. This also ties into the need for some sort of smart repository management, preferably machine linking. Published formats are very important. Whether it's a standard or whether it's an internal published format, having some sort of data that is just esoteric data is really, really hard to deal with, especially if you're a different team. Tooling needs to accompany that data and needs to grow with that data if that data is changing. There is a question that you have that you need to answer up front, which is centralized versus decentralized. Are you going to put all of your data in a database and put a web front end on it? Are you going to put it on in files on a branched Git system, which is decentralized? Either way can work, but there are pros and cons to each side. So basically it's trying to get all of that data in one place and how that affects the rest of the system. Next. The next tenet that I want to talk through is visibility. So understand the entire state system as well as possible in a simple way with low effort. So obviously there's a lot that's packed into that. But every complex system always benefits from increased visibility. If you are able to take a black box and turn it into a gray box, or a gray box into a white box, where you're able to say, oh, that's exactly what I wrote in code, and that's exactly what I see, whether that's timing, whether that's packet inspection or pull requests. The point that I'm trying to make here is good visibility is always worth the upfront effort, even if it is a lot of effort to get there. Next. So key takeaways. At each checkpoint, you want to be able to understand not only your configuration, which can be code, can be your startup state. I mean, a lot of things that Peter just talked about with the initialization state, that kind of thing, but also your runtime. So you want to be able to see every single transaction that's going on in the system in as much detail as possible. To do this well, you need tools that are in standard/available locations. Everybody needs to know where those tools are, and everybody needs to use them. Standard formats. We talked about that with the data deduplication. Standard dependency chain, this is where you get into virtualization like Docker, Anaconda. There's plenty of things, of papers and talks out there on this, but you want everybody to use a tool to visualize, and that tool to be exactly the same and have replicatable output. Python on one computer doesn't necessarily mean it's the same Python on the other computer. There's a lot of dependency management, and virtualization of your dependency chain really helps there. Command line is necessary. I claim that GUI is optional. As long as you are getting the data to the developer correctly and you are able to capture that data in a replicatable sense. So this plays really importantly into your pipeline and being able to run through your virtualization, or sorry, being able to run through your checkpoint and basically understand the state of the system and capture that state. Not just say, oh, well, I'm looking at a GUI and things look good right now. Well, if you go up and get coffee and come back, that GUI doesn't necessarily have a log of everything that you need. It's really important that it's command line. It's really important that it's logging. And it's really important getting back to the machine has to be able to run this. And the last thing is propagate failures. Tooling should always tell you if something went wrong and never fail silently. Force yourself to fix things early. Don't let it linger. Next. The last one is tightening the feedback loop. So this kind of pulls in all three. So you basically are setting the speed of check-ins with small bytes. You are able to visualize and understand what's going on with that visualization mantra. Once you get so the tightening the feedback loop, you do a check-in, you understand what the state of the system, it should give you a pass-fail. It should tell you, yes, this worked, or no, it didn't, as quickly and efficiently as possible. So based on that, you should be able to change one parameter, not have to go change 5, and then retest as quickly and efficiently as possible and see that your change worked. So essentially, it's trying to get that automated pipeline, automated pass-fail, and I mean, it's just trying to get you feedback faster. This is really hard. It takes a lot of effort to get a good pipeline running, and it takes even more effort to maintain through the life cycle of the mission. Again, as you start going through from the emulation stage, through hardware, through spacecraft and INT, all of these things are changing from under you, and you have to adapt. Next. So catch things at as early as possible, because cost increases as you go. So an example pipeline, and you can see cost as time here. Every commit, you compile and unit test. Every time you merge, you run application tests. Every night, you run system tests. Every weekend, you run all of your tests. So as an example pipeline there, you can see that it basically rises appropriately with the amount of effort that goes in. So it's able to catch more and more and more as you put more time in, obviously, but you don't have infinite time to throw at every single checkpoint. And that's something that you have to essentially work through, and that will change throughout the mission. When you think emulations at the beginning, you can run all of your tests because you just don't have that many tests. And then your pipeline starts running 2 hours long and you're committing every 15 minutes. Well, you're just going to fall behind. Lay out a framework that you can build into with as little effort as possible. Even if you build a perfect framework, other things, environment will change, and it takes effort to maintain. But you want to have like a bucket that automatically pulls up tests. If I just put another test in my development environment and I commit it, then it'll automatically get picked up by my pipeline. consolidate test frameworks. So on Dart, we started with Cosmos. Cosmos was wonderful. We really enjoyed it. It has a really nice testing framework, but that's not our end ground system. And so at some point during the mission, we had a schism. We had to say, okay, all of the tests that we built for Cosmos, we can't use anymore. We have to port, or we have to basically just say that they're lost causes and move on. So consolidating your test frameworks is really, really important. False positives are unacceptable. You want to be able to absolutely 100% trust your pipeline. When the pipeline says that your code is good to go, then you should be able to deploy it to your spacecraft. If you have any false positives, then you, SMA, everybody will start distrusting what your pipeline is producing. False negatives, on the other hand, while they don't necessarily detract from the ability to deploy when things are green, they will cause you to chase down significant amounts, spend tons and tons of time chasing down problems that are not really problems. So the environment changed from under you. Well, that's not necessarily the flight software that you're trying to test's problem, but it is an environment problem, and you are going to spend hours chasing that down instead. Get feedback from machines, so the automated pipeline, but get feedback from people too. We embedded a developer with the Draco team. We embedded a developer with the Next C team. We embedded a developer with the GNC team. And because we had those bridges, we were able to get that not only, hey, we're building the right software because the pipeline says we are and our testing says we are, but we're building the right software because the end user says that we are. And that is really, really important, to continually get feedback from the people that are actually using your software. Next. So did it work? Yes, I think that it worked very well. Our response time changed from weeks to days if we needed to quickly respond to a problem. The one-shot acceptance test turned into nightly and weekly regression suites. We came in ahead or on schedule for every major release. And we, like the flight software team, provided a lot of visibility into other subsystems problems that was not there before. And a lot of that was the tooling. A lot of that was the integration with other subsystems. And a lot of that was that data de-duplication, because every subsystem had their own copy of that number 15. And as we consolidated, we actually just solved problems at compile time. It was a large effort. It was 30% of the Dart flight software effort. And that we even started with a legacy flight software base. Tooling and automated testing is not easy. And it's easier when you start from it's easier if you go in with the mindset that you're going to already do that for the tests, but it's something that you just have to be aware that it costs money and you need to plan for that. And it's a large mindset change. Your entire team needs to buy into the fact that they are building tests to be automated, not to be manually run. And for them to check in their code when they're done with that small amount of work that they did, not let it linger for a day or let it linger for a week. So where can you start? Identify the bottlenecks in your current setup. So how far apart are your checkpoints? Are your checkpoints involving multiple different pieces of state change that you should be testing individually? How replicated is your configuration? Can you consolidate data into a single magic number that's propagated? What are your blind spots from a visibility perspective? And how do you create a replicatable and trustworthy test suite? So understand what you're trying to tackle first, and then it's an incremental process. Every small step is worth it, but always build towards a larger framework. So spend the time to look at infrastructure up front. You might not get all the way. You might get just past the point of viability on on slide 15, but as long as you are making incremental progress, then it will continue to snowball. And I think that that's one of the big things about DevOps. It's building to the future. It is not just building to a single point solution. I think I left no time for questions. I am really sorry. But
well, Chris, that's the benefit of being at the end of the day. We can keep you as long as you're willing to stick around. So we do have several questions. First one, commit often. Oh, my screen moved. So commit often, early and often. Any limitations that you would impose on the commit size, pull request size, how many lines of code? I think basically, what do you think is the sweet spot for that?
So my goal is for a code request, a pull request to take 15 minutes to review. 30 minutes is kind of pushing it. And I don't really have an answer for how many lines of code that is, because sometimes they're really easy, even though they're long. But it's trying to get it down to a time perspective. So yeah, I would say 15 to 30 minutes is your sweet spot for how long it takes to do a code review, and it's based on the people doing the reviews. There isn't necessarily a per line limit.
Okay. All right. Next question from Craig. What was your experience with the transition from automated testing on PC Linux to automated testing on RTEMS?
So we had a wonderful transition. We built so the SpaceWire application was new for Dart. And basically what we did was we emulated SpaceWire over Ethernet UDP. And so every single message that we sent out was just SpaceWire encapsulated over UDP in PC Linux. And when we got to, another callback to Peter's slides, we used Kaitai. So we are actually generating our code from Kaitai. And so that handled our endianness problem, which there is an endianness problem if you're using PC Linux and then you go to something like Spark RTEMS. So if you handle the endianness problem and you have a packet-based input-output system, then PC Linux to RTEMS, we still have our PC Linux system running our normal code with our pipeline now in TVAC.
Excellent. All right. Next question. What could you not do with Cosmos?
The thing that we couldn't do with Cosmos is actually fly the spacecraft, because that's what MOPS. I mean, it basically comes down to APL is using L3 as our mission system. We don't make that call. We're flight software. And so because that was picked well before us, I enjoy Cosmos. I have not hit the limitations. So that, I mean, it basically just came down to a choice in ground system, not necessarily a technical issue.
Mm-hmm. All right. Well, let's do one more question, and then we can allow things to continue on in Slack. So Gerardo asks, how do you combine DevOps with a more traditional spacecraft waterfall approach? And how did you deal with software-hardware interfaces?
So honestly, I think that if you take a DevOps approach or some very iterative approach from a software perspective, while hardware is continuing its waterfall approach, hardware tweaks a lot. And I think that we all know this. Hardware always changes from under us, right? So the fact that we're able to respond to that within a matter of days or within a matter of weeks, instead of saying, oh man, everything changed, how do we even respond to that? I think that it gave us a huge leg up in an ability to actively understand what changed from under us and respond to it. So I think that it pairs nicely It just gives us an extra degree of freedom, if that makes sense.
Excellent. All right, so here's my proposal is I think it would be useful to create a DevOps Slack channel. I don't think we have anything like that. I think that there's a lot of interest in this topic. So let's create a DevOps Slack channel, and we will transition the couple remaining questions over there and continue this conversation throughout the rest of the workshop. Thank you very much, Chris, for a fantastic presentation.
Thanks all.